Speaker.
Okay, great. Thank you, Jordan. So today it is our enormous pleasure to welcome back one of our own. What we have today is Professor Yashar Hezaveh from the University of Montreal, although he got a start here at McGill, getting his PhD in 2013 here with a thesis on strongly lensed sources in millimeter wave surveys. After that, Yashar went off to Stanford in California, first as a postdoc fellow and then as a Hubble fellow, before spending a year at the Flatiron Institute, the Center for Computational Astrophysics. And then we were able to get him back to Montreal at UDM, where he's now an assistant professor and a Canada Research Chair in astrophysical data analysis and machine learning. And so Yashar is going to tell us today about probing the particle nature of dark matter with strong gravitational lensing. So take it away.
All right. Thanks, guys. I'm not muted, am I? Okay. It's really a pleasure to see some familiar faces and kind of refresh all the McGill connections. And I have to thank a lot of you guys who were around at the time I was here, and I've definitely learned a lot of things from many of you. And so I'm going to just jump into it. So the title of the talk is Probing the Particle Nature of Dark Matter with Strong Gravitational Lensing. And so this is a work that I've been doing for the past more than 10 years with a really fantastic team. Like Neil Dalal, he's at Primary Institute now. Gil Holder, who used to be at McGill, my advisor, Laurence Perrault-Vassar, who's also at UDM now, and a bunch of other names that you may recognize here. Why does this not forward? Okay, so here's the outline of the talk. First, I'm going to start by talking about strong gravitational lensing, introduce what lensing is, and then we're going to talk about dark matter and the small-scale distribution of dark matter and some of the problems associated with it. Then we're going to talk about strong lensing and how strong lensing can provide a solution for these problems with dark matter. Then we're going to have a look at the new generation of lenses being discovered, ALMA, and a new analysis method. And then we're going to specifically look at lens modeling, which is kind of like the analysis methodology for setting gravitational lenses. We'll have a look at the first results from ALMA, and then kind of like after that, we're going to go more towards the future and see how in the coming years we're going to have more data to help us constrain the properties of dark matter, and then kind of like more long-term future with machine learning and LSST and new generations of surveys in the sky. So I'm going to start by introducing strong gravitational lensing. Strong lensing is the formation of multiple images of a single distant object due to the deflection of its light rays by the gravity of intervening structures. So like here, imagine that, we are, can you guys see my pointer?
Yep, no problem. We can see it.
So, we have like, the Earth here on the left side, we have two galaxies, one kind of like placed behind the other one. And as the light rays of the background galaxy, the red galaxy, they travel and they kind of like pass near the foreground galaxy, they get bent by the gravity of the intervening galaxy. And so as a result, they come to us from different directions. And so we see multiple images of these background sources around the lensing galaxies. And it's very similar to what we see in a fish tank. If you look at the fish tank from the corner, we see two images of the same fish. And so the reason is that, I lost my pointer, but the reason is that, so the light rays from the fish, they come from the two sides and they get refracted. So they come to us from two different angles. And so we see these two different images. Here's a good example of that. Here's Mr. Mango, a fish we had like years ago. And so as he goes to the corner, you can see that we're seeing two different images of the fish at the corner. And although that looks very easy, it's much harder to actually be able to capture it on camera after a long time. So we see the same thing with with strong lensing. So here you're looking at an image of a background source that's been strongly lensed into these two different images. So in the middle, you're looking at the lensing galaxy. That's the orange galaxy that you see in the middle. And on the two sides, we see two different images of a background quasar. And so the major difference here between strong lensing and gravitational lensing and the fish tank scenario is that here the deflection of the light rays is done by the gravity of intervening structures instead of refraction. But quite often when we look at strong gravitational lenses, instead of just two simple images, we see these kind of arc-like images. And the reason for that is the geometry of the lenses, the kind of like more spherical geometry of the lenses. And to reproduce images like that, what you could do at home is just kind of like have a candle and a wine glass. If you get an image of a candle, if you just put a candle flame in a dark room and get a wine glass and look through the foot of the wine glass at the candle, you can see that the image of the flame kind of like wraps around the foot of the wine glass, and it produces these arcs very similar to what we see in strong gravitational lensing. So here on the left, you see an actual image of gravitational lens horseshoe with Hubble Space Telescope. So in the center, again, you see the lensing galaxy. Around it, the arc is the lens background galaxy, which is at a much higher redshift. So when we study strong lenses, we typically are interested in three main categories of sciences. Either we study the background source, or the foreground lens, or sometimes we just use the whole system to constrain cosmological parameters. So for the background source, we typically use strong lensing as a cosmic telescope. And that's because lensing magnifies the images of these background sources and makes them appear brighter. And so this allows us to study some of the most distant galaxies of the universe that kind of like would have been below our sensitivity or resolution limit otherwise. And so this is a work that, we've been doing within the SBT-SMG collaboration for the past more than 10 years, where we study the farthest galaxies of the universe. And it's only thanks to strong gravitational lensing that we can observe these like very faint and very distant sources. But alternatively, we can use strong lensing to probe the distribution of matter in the lensing structures. And here, the idea is that the distortions in the images are caused by gravity in the lensing system. So we can use them to map the distribution of matter in the lens. And this is particularly useful when we want to study dark matter. And the third thing that I wanted to mention is that we could also use the whole system to constrain cosmological parameters. And one of the key ways to do this is to measure what is called the time delay between the different lens images. So as the light rays, they go through the lensing galaxies, they come to us at different times. And that's because the path that they travel is different. And also there is a general relativity effect of time dilation here. And so if the brightness of the background sources are kind of like fluctuating and variable, if we do a kind of like monitoring campaign, then we can measure these time delays. And that allows us to measure the Hubble constant. I won't be talking much about this particular thing today, but at the end of the talk, I'll just kind of mention a project that we're starting to use strong lenses to measure the Hubble constant. So whatever these sciences are that we want to do with strong lensing, there are typically three key ingredients that we need to have to be able to accomplish our science goals. And the first one is that we need to actually find the lenses. And this is not always trivial, because strong lensing is a quite rare phenomena, and typically the probability of getting lensed by another galaxy is about 10 to the minus 5. And so we need to find the lenses, figure out where they are in the sky so that we can actually go and observe them. And once we know where they are, of course, we need powerful telescopes because we need to kind of get high quality data of these lenses and follow them up. And finally, we need to know how to analyze the data. And so we need analysis methods that are kind of like tailored for strong lensing to figure out how to measure the physical properties that we're interested in. And so kind of in this talk, I'm trying to talk about the small scale distribution of dark matter. I'm going to try to put it in the same kind of like in the context of these three elements of discovering lenses, follow-up observations, and analysis methods. So I'm going to kind of take a step back and talk about the small scale distribution of dark matter and why it is interesting. So the past 2-3 decades, we've really measured the large-scale structure of the universe with accuracy and precision. And we found that the large-scale structure closely matches the predictions of the simplest dark matter model, the cold dark matter. But when we zoom in on one of these kind of like halos, like, if you're looking at this simulation on one of the halos of kind of like galaxy-size, dark matter halos, the consistency between predictions and observations is less clear. And so this small scale distribution of dark matter is not quite well understood, and it has become kind of a hot topic. And part of the reason for that is the discrepancy between the predictions of cold dark matter models and the observations of dwarf satellites of the Milky Way, of our own galaxy. So specifically, cold dark matter simulations predict that the halo of galaxies like the Milky Way should be composed of tens of thousands of dwarf subhalos, like the image that you see on the left here. And if you assume that each one of these subhalos hosts a tiny galaxy, then we expect to see thousands of dwarf galaxies around the Milky Way. But in reality, in the past 2 decades, a lot of deep searches have found that only about 50 satellite galaxies exist for the Milky Way. And so this discrepancy has been called the missing satellites problem. And so this is kind of an outdated plot from Luis Rigari in 2007, so where he shows the number of dark matter subhalos in simulations on the the red curve, and the number of observed satellites of the Milky Way. And so the number of discovered satellites has come up a little bit more now, but there's still a huge discrepancy, about 2-3 orders of magnitude. And as you can see, it gets worse as we go to lower masses. And so there's been kind of 2 solutions proposed for this problem. So in the first one, these dark matter subhalos exist according to CDM, but we simply can't see them because they don't host any galaxies in them. But alternatively, it is possible that we don't see any galaxies because there's no stars and no subhalos. And so if that's the case, then we need to modify our dark matter model. And there are alternative dark matter models like warm dark matter that have exactly such prediction. So in this case, the dark matter particles have a non-zero thermal energy, which results in them kind of erasing the small scale structure in the early universe. And so they're smoother on very small scales. So this is kind of a very simple toy model to show you, why that happens. So let's assume that in the early universe, we had two density, 2 modes of density fluctuation. So, one like this with a long wavelength, and then another one is like this with, short wavelength. And so we have a superposition of the 2 modes. And so if we have now a realization of this field, so each particle now is a dark matter particle, and if my particles have some non-zero thermal velocity, in a limited amount of time, they might manage to move around more than the wavelength of the smaller mode. And so they'll erase these perturbations. But on the larger scales, the distribution doesn't really change. And that's why both cold and warm dark matter have similar predictions for the large scale structure of the universe, but on smaller scales, they start to diverge. And so this is a plot of the linear power spectrum of dark matter. And on this side, on the left side, on the cosmic and cluster side, you see that we have very good measurements, and both cold and warm dark matter have similar predictions. But on smaller sub-galactic scales, they start to diverge. And interestingly enough, this is the regime that's not really well measured and well constrained. So if we could map this small scale distribution of dark matter, then we could distinguish these 2 different scenarios and resolve the confusion and learn something new about the dark matter particle. But because dark matter is invisible, we really need to use a purely gravitational probe to do this. And that's really the key. And as you can imagine, what we would like to use here is strong gravitational lensing. And so strong lensing, in fact, is the only known method that can do this at kind of cosmological distances. So the idea here is that if the main lensing galaxies have dark matter subhalos, these subhalos can induce tiny gravitational perturbations on the images of background sources, which which could reveal their presence. And so here's an example. Here we have a simulation of a background source. It happens to have, funny colors. This is just it's kind of a toy model simulation. Now, if we place a dark matter subhalo on the image on the top right corner, you see that that subhalo kind of perturbs that one image differently than the other images. So the other images stay relatively unchanged. And so by comparing these different images of a background source, we can infer the presence of an additional source of distortion in the image's lensing, which reveals the presence of a dark matter subhalo there. And so back to the wine glass analogy, now you can imagine that if on the foot of the wine glass, we also had a kind of like, a water droplet. That water drop kind of like itself adds another tiny, lensing distortion to the image of the candle, which we could use to infer its presence. And even in this case, exactly when you're looking at this image visually, the only way that you know that there's a water droplet there is really by just kind of like your brain is looking at the distortion in the image and making that conclusion. And that's exactly what we can do with strong gravitational lenses, except that the effect here is much more subtle. So to give you a sense of the numbers, the main host galaxies have masses of, order of 10 to the 12 to 10 to the 13 solar masses. But their satellite subhalos that we're searching for have masses between 10 to the 7 to 10 to the 9 solar masses. So they're kind of like, 5, 6 orders of magnitude, less massive. And so they result in very subtle image distortions. Here, I've made 2 different simulations, one with and one without a subhalo. And you can see that it's nearly impossible to spot any difference between them by just looking at them. But, there is a difference, and, I'll come back to this in a little bit to show you. So this is not a new idea. So this kind of like game started in 2002 with Alan Kochanek, where they analyzed a sample of 7 lenses, and they got some constraints that were consistent with CDM, but with kind of large error bars. And in the years since then, a few different groups have tried to do it. But now kind of like, almost 20 years after, we still haven't significantly improved on these constraints. And the primary reason for that is that we haven't had enough sensitive lenses. And, oh, I went back up. And so, but now it's kind of like changing thanks to these 3 factors that I mentioned earlier. First, we have discovered a new population of lenses that gives us a lot of statistical power. And second, we have a new powerful telescope to study them. And finally, we have new accurate analysis methods for this problem. And I'm going to kind of like go through these and talk about each one of them one by one. So in 2013, we announced the discovery of a large population of lenses that were detected with the South Pole Telescope. And a few other wide field millimeter surveys like Herschel and ACT and Planck have also found similar lenses. So with these lenses all together, we found a few hundred lens systems, almost doubling the number of known lenses from before. And so we wanted to know if these population of lenses could be useful for detecting subhalos. And so what we did is that we performed a Fisher forecast to estimate if we could expect to detect any subhalos in one of these lenses. So this plot is showing the cumulative average detection rate as a function of subhalo mass here. So on the x-axis, you see the subhalo mass. And these different curves kind of like correspond to different assumptions for the system and for the background and the foreground source. And so amazingly, we found that typically we should expect to detect of order 1 subhalo in each lens. And so given that we have hundreds of lenses, this is really a great opportunity to have a statistical census of the subhalo abundance here. So we thought we had the lenses, check. And for telescopes, we have to say that, and ALMA is perhaps the most powerful telescope for observing these sublunar sources. And so the discovery of these lenses coincided with the operation of ALMA, which was really, really fortunate. And so ALMA is a revolutionary interferometric array composed of about 66 dishes. And it started kind of like pilot operations in 2012. And that's where we got the first batch of data for the SPT lenses, and was finally complete in 2015. And so being an interferometer, ALMA actually measures the 2D Fourier transform of the sky emission. So every pair of antennas measures a single Fourier mode, and which we call a visibility. And so with a bunch of these antennas, we can measure some of the Fourier modes, like the red points on the right side here. But if we place these telescopes, close to each other, the antennas close to each other, in what we call the compact configuration, we can measure the modes that are kind of like low frequency modes. And so if we take the inverse Fourier transform of the image, we take a low quality kind of image, like the one, or low resolution image. But if you place the antennas far from each other in kind of like what's shown in the below, in the extended configuration, we can sample higher frequency modes. And so if you take the inverse Fourier transform, we get a higher resolution image. And so in the first few years of operation, ALMA was only operating in the compact mode, in the kind of like short baseline mode. And so we had images of, with resolutions of about typical, like, 0.3 to 0.5 arc seconds. But during the long baseline campaign in 2014, ALMA went to the most extended 16-kilometer baselines and observed the Herschel detected strong lens system, STP-81. And so for the first time, we went from these kind of like half arc second resolution images to this beautiful image of a strong gravitational lens with resolution of about 20 milliarc seconds. And so this image that you see here is a composite image of the stellar light in the lensing galaxy, that's in blue from HST. And the red here shows the ALMA observations of dust continuum in the background source, which is at redshift 3.5. With such kind of like high resolution images, we thought that it was definitely possible, with the simulations that we had, we thought that it was definitely possible to detect these dark matter subhalos in lenses. So telescope checked, and then how about the analysis method? So the question is that, so we have these like fantastic, data, how can we detect these tiny dark matter subhalos? And to answer that question, we have to first talk about how we measure any physical properties from images of strong gravitational lenses. And so we do that by kind of like, first of all, all of these physical properties that we can constrain, we call them like lensing parameters. And so there are typically two classes of these lensing parameters. There are parameters that define the morphology of the background source. This is like the true undistorted image of the candle. And then there are parameters that define the matter distribution in the lensing galaxy. And so these two completely define a lensing system. And so to see that, like, just consider the problem of simulating a gravitational lens. If I were given an image of a candle, like the one on the left here, and a foot of a wine glass, and if I wanted to produce a simulation of a lensed image, all I have to do is just get the foot of the wine glass, run a ray tracing simulation, which basically tells me how every pixel is distorted. So I get a vector field. It's the field of the distortion. It's basically a coordinate transformation. And then all I have to do is just get the image of the lens, the candle, and move every pixel according to this vector field. So I get a lensed image. But when we have data, we have the opposite problem. We have this lensed image, but we neither know what the background source, the true image of the galaxy or the candle in this case, nor what is the distortion that's been added to it. And so the problem here is that we actually don't know the inverse of this simulation process. And so we solve this problem by kind of like, model fitting, which means that instead of like undoing this, what I do is that I just try to produce a lot of simulations from a lot of different combinations of, candles and wine glasses. And if I can produce a simulated image that really looks like my observed image, then I can infer that the parameters that I chose, the parameters of the background source and the foreground lens, are the kind of like consistent with the observations. And to do that comparison to see how similar these are, of course, we use a likelihood function. And this is why this is called the maximum likelihood lens modeling approach. So when it comes to ALMA data now, remember that we said that ALMA doesn't actually produce an image, but we measure these Fourier transforms of the image. So all we have to do is that in our simulator too, just take the image, take its Fourier transform, and predict these Fourier modes or divisibilities, and then form our likelihood function in that space, which could be a lot more accurate because the noise in that space is a lot more simple and Gaussian and uncorrelated. Now, when it comes to detecting subhalos, all we have to do here really is to compare two different models, one with a smooth mass distribution in the lensing galaxy with another one with one or multiple subhalos to see really which one is a better description of the data. So this is kind of like easier said than done. The problem is that, specifically for ALMA data, we have millions of these visibilities and tens of thousands of parameters. And so this kind of results in dense linear algebra operations on terabyte-sized matrices. And so our solution was to develop ripples, which was this distributed pipeline to do these computations, using MPI on thousands of cores and allow us to do these calculations. We have extensively tested the pipeline on a large number of simulated data. And here you're looking at the results of two of these simulations. So on the left side, we're looking at a simulation where there are no subhalos in the lensing galaxy. So we're showing the arcs with these kind of like white contours, and there's no subhalo in the data. And the grayscale is showing the results of our search for a subhalo. So anywhere that it's black, we're ruling out the presence of a subhalo with a significance equal to the square root of what you see in the color bar. So anywhere that's black, we're ruling out the subhalo at 5 sigma level. And so there are no subhalos, and we don't detect any. On the right side, you see there's a subhalo at the place where there's the I don't know if my pointer has kind of disappeared, but the blue dot, and the red region there is showing the detection of a subhalo in the pipeline. So there are kind of like two things to take from here. Is that one, when their subhalos are not there, we can rule them out. We can actually kind of like with the significance that we have, we can just rule out the presence of the subhalos. And when they are there, we can actually detect them. So back to this image that I showed you earlier, we said that it's really hard to visually see what's the effect of a subhalo. If I actually kind of put them on top of each other and blink between them, you can see the tiny, tiny effect of a subhalo. So the red cross that you see there is the position of the subhalo. And we're kind of like blinking between the two different images. And you can see very close to the subhalo, there's a tiny, tiny distortion in the image of the background source, in the lens image of the source. And so if you actually produce a simulation of this with realistic noise, realistic antenna phase errors of ALMA, and put it through the pipeline, marginalized over all the unknowns, we can actually get a very significant detection of these signals in our pipeline, like you see here. So analysis methods check. And so let's kind of like see what happens when we put all of these together. So this was our detection of a dark matter subhalo in the first analysis of this data set on SCP-81. So we detected the dark matter subhalo at the location kind of like marked by these contours. Those are the 1, 2, 3 sigma confidence regions of the detected subhalo. And this was a detection of a 6.9 sigma. And so here you're looking at the marginalized posterior describing the mass distribution in the lensing galaxy. And the last 3 columns are showing the log of the subhalo mass and its position, which is 10 to the 9 plus minus 0.1 dex. And so not only can we detect these subhalos, but we can actually measure their masses. And so as I mentioned earlier, in addition to finding subhalos when they're there, we can also rule them out if they don't exist over the regions where we have sensitivity. And so these different panels are showing the results of our search at different masses from kind of 2 times 10 to the 7 to 10 to the 9 solar masses. So by combining the detection of a individual subhalo and these exclusions, we can work out our limits on the mass function of the dark matter subhalos, which are these errors and error bars. So this plot is showing the projected number of subs. And for comparison, the gray band here shows the kind of like previous measurements of phthalate and Kochanik from the 7 lenses scaled to this particular galaxy, which are also consistent with CDM models. Now we can try to compare our constraints with CDM predictions. And this is one such comparison from Fiacconi. And the error bars here are limits from SCP-81. And the shaded regions show the abundance of subhalos in their high resolution n-body simulation. So right now we're kind of in general agreement with CDM, but we really need to be able to increase our precision to be able to distinguish between cold and warm dark matter models. And I'll talk about that in a few minutes. So the question is really, how do we improve these constraints? And so on the shaded area here, where we have good sensitivity, we're primarily limited by the Poisson shot noise of subhalos being in our images or not. And that's why we're going back to ALMA to observe more sources to improve our statistics. And so in this target, just kind of like you can see that, there's like really fantastic data. These are data from ALMA of 2 additional sources. The one on the right, we have approved JWST proposal for this in the early release science program. And so it's going to be really exciting to kind of combine these different data sets and get the constraints from these. So the question is, how much better can we do? And in this plot, what we're doing is that we're showing the same mass function and these different warm dark matter models. So the dashed lines are the dark matter models here. And the solid line here is the prediction for CDM. And so the blue region is our current constraint from a single system. And the yellow region is our projected precision with a sample of 40 similar lenses, with the CDM kind of assumed as a fiducial model. So we can do these sort of calculations to calculate the warm dark matter model that we can rule out at 2 sigma for a different number of lenses. So this plot shows these constraints as a function of the number of lenses that are in this study. And so we're kind of expecting that, as we increase the sample size, we're going to kind of like push it to higher mass warm dark matter models. And this is kind of like what's my prediction for what we can do realistically in the next few years. Kind of like, we stand, somewhere around here now. And in the next, I hope 2-3 years, we can kind of like, push this to a few keV. But really the game changer here is going to be a large number of lenses from services like LSST and Euclid that are coming actually quite soon. And I'll kind of talk about that a little bit towards the end of the talk. But in addition to targeting new lenses, another thing that we can do is to try to push our sensitivity to even lower masses. And it's true that I cannot detect an individual subhalo with masses much lower than this limit here that you see. But according to CDM, there should be tons of these smaller subhalos all over my images. So the question is that, can we detect the collective signal of a large number of these subhalos together statistically? So now, instead of looking at a tiny water droplet or the effect of a tiny water droplet on the foot of a wine glass, just think about frosted glass. So when we look at frosted glass, we notice that the images are highly correlated. And so the shape and the size of these correlations kind of like tell us something about the shape of the glass. And so we can do exactly the same thing with strong lenses. And by measuring the correlations in the surface brightness of the backgrounds of the arcs, we can measure the power spectrum of the density field by treating it as a random Gaussian field here, basically. So I'm going to take a moment to talk about like what this power spectrum actually tells us about the population of lenses. So this power spectrum is for a population of point sources, point masses. If you assume that the masses were point-like, they would be just a flat line. And the amplitude of the power spectrum tells us something about the total abundance of these subhalos. So by basically measuring a single number, we have basically a handle on the collective, impact of all these lower mass subhalos. But if the subhalos have, a kind of like extended density profile, like we expect them to have, like an NFW profile, then we're cutting the power on the high K mode. And so the shape of the power spectrum also tells us something about the shape of the density field and the density profile of these dark matter subhalos. So we wrote this paper a few years ago to show how to write a likelihood function to measure these the power spectrum of the density field by measuring these correlations in the images. And we had a Fisher forecast to have a prediction for what could be actually measured with these lenses. So here, what you're looking at in black is the power spectrum of a cold dark matter model from Via Lactea 2 simulation. And the error bars are showing the prediction for a measurement of the power spectrum in a single source with like, a 10-hour and 40-hour integration. So these are kind of different predictions. And like I mentioned, if you could just measure that one number, the error bar on the left, the amplitude, we're basically measuring the effect of these much lower mass subhalos that we cannot detect individually one by one, but collectively they're affecting our images. So I'm going to kind of like move along now, kind of talk about the future and look into the future and talk about new lenses, new telescopes, and new analysis methods. And perhaps the most exciting thing here to say about future is that we're going to have a lot of new lenses that will be discovered in the next decade with big surveys like LSST and Euclid. And so in particular, LSST and Euclid are predicted to discover more than 100,000 lenses each. So all of a sudden, strong lensing samples are going to go from like a couple hundred to a couple of 100,000. And this is really exciting because of the statistical precision that like such large number of lenses can give us, and also for finding like rare systems like lens supernovae and double plane lensing and all sorts of exotic things that can allow us to measure very interesting things. And of course, there's going to be no shortage of powerful, follow-up, telescopes. So, ALMA is already here. GMT and TMT hopefully will come towards the end of the decade. JWST will be coming soon. I think at some point, I used to just put year after year, change JWST. I just put question marks. So, but the real challenge historically was the analysis method. And so the question was, how can we analyze 170,000 lenses? And so lens modeling is very slow. And even, the analysis of a simple lens could take, quite a few days of, somebody working on it constantly. And so, with so many lenses coming, there was this sense in the community that, we'll never be able to analyze all these lenses with these traditional methods. So the methods were just like simply not scalable. And so this kind of like motivated us to look into the use of machine learning to speed up these calculations. And in particular, the use of neural networks. So I think most of you are now familiar, but I'll just mention briefly that neural nets are these computational structures under the general umbrella of machine learning, and they process their input data by multiplying it by these matrices that are called the network weights. And so they produce an output of interest. And so they do this mapping, and the values of these weights are determined through a process called training. Where we show the networks kind of like a bunch of examples for which we know the correct answer. And so what's really fascinating about neural networks is this universal approximation theorem, which states that under certain conditions, a neural net can approximate any function to an arbitrary accuracy. And so remember that part of the really difficulty for us to model these gravitational lenses is that for every one of these data sets that we have to produce tens of thousands and millions of simulations to be able to produce a simulated image that really looks like the observed image. And that's because we didn't have this inverse function of our simulator. But with neural networks, we can actually construct this kind of inverse function. And so now I can just like put my observed image and directly have a prediction for what the background source and the foreground lens are. There is a particular flavor of these neural nets called convolutional neural nets that are kind of adapted to image processing problems. And typically they are used for classification problems. So they would look at an image and say if it's a bird or a cat or a dog. And they do this by filtering the image with filters that they will learn. And so a few years ago, people started doing the same thing with strong lensing to discover strong lenses, because that was also a challenge, how to find these strong lenses in these large surveys. But what we wanted them to do was slightly different. So we wanted them to actually get these lens images of background sources, put it through the kind of like multiple layers, and at the end of the network, have a prediction for these kind of lensing parameters, like the mass distribution, the lensing galaxies, or the structure of the background sources. So we did this by first producing a large training set. So what we did is that we got tens of thousands of real images of galaxies and lensed them with simulations, added also, sorts of like observational effects like blurring with a PSF, various forms of noise, Gaussian noise, Poisson shot noise, cosmic rays, and all sorts of things. And then we train networks to be able to predict these parameters. And so we trained multiple networks, and surprisingly, the training was, pretty short, 1 to 2 days on a single GPU for each model. And so once we trained them, we kind of like tested their performance on 10,000 simulated images, some of which you see here on the left side, and 9 real HST images of gravitational lenses with previously known lens models. And so here are the results of these kind of tests. What you're looking at on the y-axis here are kind of like the predictions of the networks for a particular lensing parameter. On the x-axis, you see the real value from the simulations. And for the real data sets, the x values are the previously published parameters for those. And so the kind of dark and light kind of like shaded regions, the blue shaded regions here are showing the kind of 68 and 95% regions for these tiny points that are the 10,000 simulations. So it's pretty clear that we can actually detect these, kind of measure these lensing parameters from, by, using deep learning. What's really exciting about it is that we can do this like 10 million times faster than in maximum likelihood lens modeling. So the evaluation of a single model would take about 1/100th of a second on a single GPU, as opposed to many, many days. And so all of a sudden, the analysis of these LSST data, instead of like a 1400-year analysis, kind of like becomes manageable. You can do it like in half an hour on a single laptop. But the other question at the time was, how about the uncertainties of these models? So kind of like historically, like most deep learning and neural net models, kind of they had point estimates for whatever they were doing. And so there's like different ways to go around this. But one thing that we can do is that to actually make the networks predict their own uncertainties. And so here, the first thing that we did is that, instead of predicting a point estimate of the lensing parameters, make these neural networks predict kind of a distribution defined by, a handful of parameters. For example, we can use a Gaussian distribution and have the networks predict the mean and the variance of the distribution. But then the other thing is that these networks kind of like they also make an error in their own calculation of their uncertainties. So how do we actually marginalize over that? And we did that with Bayesian neural networks. So these standard neural networks have weights that are deterministic and fixed. And so during the training, you just come up with a fixed number. But in Bayesian neural networks, we can actually replace these weights by kind of like a probability distribution. And so during the kind of like testing, or during the inference time, we can actually marginalize over these parameters of the network and basically marginalize over those added sources of uncertainty in our predictions. So this is an example of what we did with this. So here on the y-axis, you're again looking at the predictions of the network for this lensing parameter. The error bars here are showing the 68% regions of kind of like these the networks as a function of their true value on the x-axis. And so one thing that we did was that we kind of tested how accurate these uncertainties are. And to do that, we measured the coverage probability of a confidence interval, which is kind of the proportion of the time that that interval contains the true value of interest. So we can just repeat this in a you can do this both in a Bayesian term and a sense and a frequentist sense, so that you just repeat the experiment and see how many times your true value actually falls within your 1 sigma region. And so hopefully 68% of times that should be the case. And so we realized that, that requires basically some tuning and basically calibrating. But by calibrating the network with a single parameter, we can actually get 1, 2, 3 sigma regions that are accurate and that their coverage probabilities match their confidence intervals. Another approach to estimating the uncertainties, though, is what is called kind of like the general umbrella of likelihood-free inference. As you hear, the key idea here is that we can actually run a lot of simulations and figure out basically what is the range of possible outcomes from the simulation that our prediction has, and basically that will kind of define our posterior. I'm not going to go much into the details here, but we've done some tests here to show that actually we can get the joint parameters of these joint posterior of these parameters very accurately by doing these likelihood-free inference. And in fact, likelihood-free inference, it has to say that actually, in under certain conditions, it actually approaches the posterior of the predictions that we have. So it's really an exciting thing that we're working on right now, and maybe I'll be happy to share the results of that, in the coming years with you guys. Another thing that we did was kind of the reconstruction of the images of the background sources. I mentioned that we had the predictions of these like simple parameters, but another work that we did with Warren Morningstar, who was a graduate student at Stanford at the time, was that to get these recurrent neural networks to make it a prediction of the kind of background source. And so we do that by basically using these neural networks as some sort of like optimizers that have the capability to learn very complex nonlinear priors. So the outcome of this is that we just get these observed images, we put them through this recurrent inference machine and produce a reconstructed source. You can see the result here, and when I just blink here, you can see the true source. So you can see that we can do a really reasonable job at kind of like doing these reconstructions. And in fact, this is a really interesting regime because the neural net predictions here are actually better than kind of like traditional kind of maximum and posterior methods here. You can see that here in this plot where we're showing the coherence spectrum at different scales. So what you're looking at here is kind of like how similar the reconstructions are to the actual the ground truth at different kind of like spatial frequencies. And so the closer to one that we are, the better we are doing. And you can see that the recurrent inference machine is doing much better than these like kind of linear inversions. And that's not magic. That's because they're actually better at learning these kind of complex priors. So when we're writing these linear inversions, we have to assume that the source is only defined by its like power spectrum. So we're galaxies are not Gaussian. There's kind of like definitely like a lot of non-Gaussianity there. So there's a lot of information. And so these neural networks can do a more accurate job because they're learning these kind of like more complex structures in the data. And then another kind of question that we had for this was that how well would they do kind of for like out of sample examples. So we trained this model on only images of galaxies, and then we said, hey, what if I just get an image of text, lens it, add noise to it, and then put it through the model? And surprisingly, we could actually get really good reconstructions, even for something that looks so different. And so it's kind of like showing. Now I'll share another example in a minute. That these models are able to actually learn through like appropriate training to learn the structures in the data that actually define the process that we're interested in. So I'm going to skip some of these. I don't know if you have a lot of time, but I'll kind of like mention this, which relates to what we're talking about right now, is that in the work that we did before, we were kind of like for the foreground lenses, we were predicting the parameters of a relatively simple model. So let's say, there's two galaxies, one galaxy is lensing the other one. So the parameters of the foreground were kind of like simple, X, Y, some ellipticity, external shear. It could be defined by like 5 to 7, 8 parameters. But sometimes we have these kind of more complex systems like the one you see here, where you have group lensing or cluster lensing. And so how do we deal with that? And so one thing that we started doing was to say that we can actually train these networks to have a prediction for the true density map. So instead of just like having a simple vector of these parameters, it can actually produce a map of the the density field here. And so this is what you see here. So basically, the network gets the image on the left, that's the observation, and then processes it to get the the prediction on the right, which is the log of the projected density. And the ground truth is here, in the middle column here. But what was really interesting is that we trained this network with only 2 galaxies. So all the training data was just like always 2 galaxies doing the lensing, like you see here, some examples. So there's only 2 galaxies doing the lensing. That's all the training. And then we stop, training. We're not training anymore. And we showed the network some cases where we have 3 galaxies. And if any of you have ever thought about strong lensing or have some experience with it, is that it's an extremely nonlinear problem. So once you add the 3rd galaxy, the image configurations, they go completely crazy. I have nothing to do with the 2 galaxy image configurations. And yet in many cases, the networks could actually predict these like kind of like three galaxy configurations, even though they had never ever seen anything like that. And that was really, really interesting because it just kind of like was showing that that even though they don't really understand physics, but they're actually learning a very fundamental relationship in the data that we're interested in. So I'm going to kind of like try to wrap up here, but just wanted to advertise a particular project. So we have this new project called Future Lens, and this is a project that was recently funded by Schmidt Futures Foundation for the development of a machine learning pipeline for LSST. And in particularly, the goal of the project is to measure the Hubble constant through the measurement of the time delays from gravitational lenses, so with machine learning. And so just a note about what LSST is. LSST is a new survey which will start in kind of like 2023. That's the current schedule for first light. And it will image the entire visible sky every 3 nights, and it will give us that kind of like temporal information that we need for transients. And so it will produce a kind of a movie of the sky over 10 years. And so this opens many possibilities for transient astronomy. And at the same time, with the humongous data that it produces, it poses a monumental data analysis challenge. So it produces about 15 terabytes of data every night for a total of about like 200 petabytes. And so, as I mentioned earlier, we're expecting to discover about like 170,000 strong lenses with LSST. And so this kind of like opens endless, opportunities for strong lensing sciences to be done specifically for us for, dark matter subhalo, mass function, and the Hubble constant. And so this is kind of like, kind of what the plan that we have for this is to build a, pipeline that is composed of, different modules for the inference of the H0, and also another group that is in New York working with us for the microlensing of the background quasars. And so we're really excited to start working on this and see where it goes. So I'm just gonna try to wrap up and say that, it's a really exciting time for strong lensing. When I started working in this field, it was kind of like, kind of patchwork of a few small groups working on a few lenses. And now it really looks like that with these big surveys coming and the new telescopes and machine learning, it's really kind of like becoming like a coherent kind of effort, in the community to do something really exciting and be able to measure these cosmological, kind of parameters with higher precision. Thank you.
Okay, thank you very much, Yashar, for a great talk. And so if you don't mind, then we've already gotten a few questions, which I can read out to you. So first, this was from Vicky when you were showing some of your ALMA results. And the question is, how do you know your solution is unique? So for example, maybe you ruled out a subhalo, but that's because your specific source model was wrong.
Yeah, that's a great question. And there is only one answer to that, and that is priors. And so it is absolutely true. I'm going to try to go back to any image of strong lenses that we have. Let's say this one. So there's always one answer that, you look at this and you say, well, there are two galaxies lensing the images of background sources and doing those arcs. And one can say that maybe there is no lensing whatsoever. There's no gravity, no distortion, no lensing. And there are just some, structures that look like arcs around the galaxy. And without any priors, that's a perfectly good solution. We can kind of like rule that solution out when we know that there's a prior, that there is, gravity. And so, once you put gravity into it, then you get to a regime where, these are like different lensed images of a single kind of, object. And so this is the most extreme case that I did, kind of like toy example that I just gave. On a kind of like more kind of like, what Vicky, would be interested about, it's true that there's always some level of degeneracy where we can make the background source a bit crazier to try to kind of like fit that signal. But remember that we have multiple images of the same background source, right? So, I have, 4 images of the same person, and one of these images looks highly distorted. So it's the comparison of this image with the other images, because lensing will kind of like locally perturb that, one image in a different way than the other images. So we can break that degeneracy. But in reality, we really need to do that very carefully. So it means that we need to fully understand our prior on what the background sources are and fully marginalize over that. And so, I have been sometimes critical of some works in strong lensing who have failed to do that correctly. And that's one of the things that has made it actually very difficult, kind of like computationally. Part of the big computational challenge that we had was actually to pixelate all these background sources, to define these priors, and to marginalize over all sorts of situations, to just say, can we account for this particular distortion by changing our background source model? And if we can, then, well, we'll just throw it out. We'll just say we don't have sensitivity there.
Okay, thank you. Deepak, I think that sort of answers your question as well, but if it doesn't, if you want to say so again in the chat, and I'll ask it. But for now, I think Jim has his hand up, so I assume he would like to unmute rather than type. Jim, go ahead.
I thought that was easier. Thanks for that nice talk. I wonder if you know if this technique has, what's its potential for discriminating self-interacting dark matter as a solution to these small scale structure problems?
So we know that there are some specific predictions in self-interacting things like the cores will be different than like in a warm dark matter model, and so kind of the density profiles, if we could measure that. Now, a few years ago, up to maybe like 2 years ago, I would have said yes, theoretically there is a signal in the data. Realistically, we'll never ever be able to measure it because it's going to be very hard. It's going to be, you will need a lot of lenses to be able to, kind of like get such a tiny signal out of it. But today I would say that, with like, if you had 200, 300,000 lenses, and with machine learning, we could really like, sift through them really rapidly. It is possible to be able to do that. I've never done, a calculation to tell you like a Fisher forecast for what could actually be done. But theoretically, I mean, there's clearly a signal just from the fact that the densities, the cores are different, or the density profiles are different.
Thanks.
Okay, so let me jump to 2 of our questions that we got from Slack. One's from Daniele. If there is this large number of dark matter subhalos in the universe, could it be possible to measure the effect on the intergalactic medium, such as on its clumpiness?
No. So yes and no, and so yes and no. So on the higher masses, yes, and that's how, say, these Lyman alpha forests, they have measured the kind of like small scale power spectrum. So you would just look at kind of the Lyman alpha forest, and just from the clumpiness of kind of like hydrogen, you can measure something. But that kind of like breaks down for a number of reasons. The first and most important reason is that at very low masses of these subhalos, kind of like baryonic astrophysics kind of like dominates and kind of like decouples kind of like the densities of baryons from dark matter. And that's part of the whole problem here. And that's why we need something like purely gravitational. So the idea here is that if you go to, a 10 to the 7 solar mass subhalo, if you have like the first instance of, a single supernova, just like the feedback from that could kind of like, push out all the gas in the thing, and it will never return. So there is no guarantee that kind of the distribution of baryons and the distribution of dark matter, have anything to do with each other. And that's part of the whole confusion about, in the Milky Way too. So the idea in the Milky Way is that these tiny dark matter subhalos maybe exist. It's just that their distribution has nothing to do with the distribution of baryons.
Okay. And Jordan would like to know if the 10 to the 9 solar mass subhalo followed scaling relations for the dust mass to halo mass or stellar mass to halo mass, Could it be directly detected with follow-up observations, say with ALMA, JWST, to empirically verify the analysis pipeline?
We would have loved for that to be true, but if you actually look at a 10 to the 9 solar mass, like subhalo, and you calculate in any kind of theoretical or empirical, relations, and see, because remember that the lensing galaxies themselves are at very, very high redshift. So, these lensing galaxies, they could be at redshift like 0.5. And so we did these calculations for JWST, and it's absolutely hopeless. But there's one thing that I have to say is that, and that would have been a really, really great confirmation if we could just go and follow them up and see. But there's one thing that we're thinking about doing is that individually, it's kind of like, seems like it's hopeless. But let's say if I have 200,000 of these, and if I say that from lensing, I know that in like every one of these, there's like subhalos of certain mass, and I kind of find out where their location are based on lensing analysis, then I can stack them on top of each other based on the location that I know from lensing. And so the question is that, am I going to see a signal from stacking? I think that would be, really fun thing to do in like 2024, 2025. So.
Okay, lots to look forward to. Let's end with Matt and then Jim.
Hey, Yashar, the description you gave of measuring the Hubble constant has the usual challenge that you're either measuring the time delay between two signals, or you're measuring the details of the lens, which is kind of hard to do. There's a new field opening in that area, which is measuring time delays exactly like that, but with radio signals from fast transients, a fast radio burst. Do you follow that? And if so, like at what level are these techniques, or are there comments about what we should be taking away from these techniques at very long time scales, or very fine reconstruction of images that carry over to the fast time domain? And here we're talking about image lags that are maybe 100 nanoseconds to a millisecond.
So Matt, I need to make sure that I understand your questions. I think the first part of your thing that you mentioned is that it's the main kind of like challenges of analysis in terms of degeneracy, what is kind of called the mass sheet degeneracy, that you have a degeneracy between the Hubble constant and kind of you can add like, a mass. Is that something that the fast radio burst could like kind of, do you have like a zero scale for mass somehow? I don't think so.
No, I think that challenge is unique to your application of that, and actually doesn't come into play as much in the fast radio burst, because in our case, the time delay is so small. What we're really trying to do is place some limit on the mass of objects. So we're probing things.
But are we talking about lens? Are we talking about lensed FRBs?
Yeah.
But I mean, lensed FRBs would still have the same issue, right? I mean, I did follow some of the papers that came. I think it was like people from Mark Kaminkowski's group like a couple of years ago. There were some papers on predictions for lensed FRBs and how they could help with this. Actually, I think the papers that they wrote was maybe for the substructure problem, not for the Hubble constant.
Yeah, exactly.
Yes,
exactly. Yeah. The only thing they're trying to measure with those types of time delays is the mass.
Yeah. No. I mean, that would be that would be definitely an interesting thing to look into. I mean, I have not particularly followed that since I read those papers a few years ago. But I would love to chat to see kind of like what are the opportunities for kind of discovering these like lensing events in FRBs, and if they could be actually realistically useful. I had an interest in these FRBs a few years ago when kind of like, I think it was 2014, 15, I chatted with Vicky once about it. But I kind of like haven't been following, more recently. So yeah, I would love to chat. But the thing that you mentioned is, another thing that I wanted to mention is that the thing that you said about Hubble constant and the degeneracy, it's true. There is definitely a degeneracy. And that was kind of part of the reason at first I really didn't want to touch this project for a while. But look, I mean, again, it boils down to having accurate priors. But one thing that we are hoping to be able to do with, again, like machine learning comes into this, is to be able to combine these different probes, like, you know, dynamical modeling and kind of like the other kind of like, you know, probes, kind of like large scale structure and the correlations and whatever, to be able to constrain those degeneracies. How well we can do it, you know, I don't know. I don't have an answer for that. But our hope is that we can kind of like, you know, what is done currently with, you know, measuring Hubble constant from lensing data is relatively kind of, you know, kind of primitive in terms of how they do the modeling, kind of like dynamical modeling of the galaxies to be able to break the degeneracy. So we're really hoping that, you know, with machine learning, we can do a lot better at getting IFU images and actually do like, you know, full, you know, kind of like modeling and other probes and kind of break that. Again, how well can we do it? You know, I don't know. But at the same time, you know, the number of lens sources, actually the quasars is less. I think the lens quasar predictions are supposed to be about like 7,000 lens quasars from LSST. But again, you know, it's a large number. So
yeah, there's got to be a lot in terms of techniques and so forth from what you're doing in the image domain that would carry over to the time domain, and not a lot of conversation yet between those groups. Cool, thanks.
Okay, so we've gone on for quite a bit with questions now. This is a great discussion. Thank you very much, Yashar, for a great talk and some great discussion. So for everyone else, if you want to express your appreciation some way, maybe with a Zoom reaction or typing on chat or unmuting briefly to say thank you, just I'll say a collective thank you, and hope to see you in person soon, as soon as possible.
yeah. Thanks guys for inviting me, for sure. And I would have loved